Yuchen, please start.
All right. Okay, but I would like to preface this presentation because I don't really have a lot of time to fully digest this paper. So there might be some parts that I cannot fully explain. And if you have any questions, perhaps we can take some time next week since I'm doing a presentation then also. We can revisit some of the concepts if necessary.
Okay.
Yeah, but I think I should have like a good understanding lah. So okay, I'll try my best. Anyway, so this is called the inflection point hypothesis. So the main idea behind it is that we create a trace of a failure execution, and then we compare it with a trace of a execution that is successful. And then from there, the first point of divergence, it's called the inflection point. And the inflection point hypothesis is simply that the root cause is the inflection point. Is that where the inflection point is? All right, so the authors, we have 5 authors. They're all from the University of Toronto.
So it's better. So by the way, in a future presentation, it is better that you find their pictures, profiles, and their research interest. That will be because especially for PhD students, when they go conference, go for some academic conference, they might meet those researchers later. So it's better that we could get familiar with them, so that we're not better.
All right, sure. I'll add it in for the next one.
Okay.
Okay, so the background is for debugging in parallel and distributed systems. So most existing debugging systems use a probabilistic approach. So they will look at the kind of predicates, which are like the conditional statements that have the strongest statistical correlation with the failure execution. And the problem with this is that it's a probabilistic approach. So we don't have like such a high confidence that, you know, whatever the system outputs is really the root cause. It's only like a good guess. And the other thing about it is that if we try to reconstruct the sequence with this method, it's quite difficult because it becomes a combinatorial problem with the try.
Will please be more specific on the buggy sequence?
Oh, so the buggy sequence is simply a sequence that leads to the failure of a program, and so like a failure is probably how it's defined as perhaps when you hit some kind of error and then the program throws an exception. So we'll see how to construct a sequence of execution such that it results in this error being thrown.
But if you recorded all the trace, the sequence is just there, right? So how can it be a combinatorial problem?
I guess it's because there can be multiple paths that lead to the failure execution, and they're trying to find one that is the most pertinent one. Like that, like there's some sequence that is the root cause. So anything after that execution will lead to the bug, and then like before that, there can be a lot of different kinds of paths.
Okay, so and also give me a sentence. They say that they use predicates that have strongest statistical correlation. So it seems they have assumption is that the bug is caused by predicates, right? So here the predicate usually, if predicate is a more academic terminology, and in essence it's just means the if condition. So suppose we write a program, and if there usually we do not carefully investigating the corner case. So usually when a great equal operation will be written with greater than operations. So this usually called predicate error or if condition error. So here you use a sentence that they're using predicates with the strongest statistical correlations. So does that mean this approach only looks into the problem or bugs in the if conditions.
Indeed. So this is part of the paper's like brief overview of existing systems. So they didn't really go into how the existing solutions actually find the bug. So
okay, please
yeah.
go on. Please go on. So this is just a background. So maybe I can be more specific on this debugging background. Usually, debugging approach is going to recommend when you have a bug there. Those kind of approach is going to recommend which execution or which statement in the program is the root cause to responsible for the final exception or final errors. So in this case, it would usually be a search problem. In the search problems, we just go through all the statements in the project or in program. They recommended if successful, and then the model or the system or the recommendation system did a good job. So here it is. So it is probably is a probabilistic. It could be using the probabilistic techniques. We assign a score representing how likely this statement is buggy. So there's a lot of one using probabilistic approach. And usually the buggy statement usually lies in the corner case evaluation. So main approach looks into the if condition or the predicates there. And here, Yuchen is talking about approach using dynamic analysis. So the idea is that it's going to record execution trace of programs and recommend specific steps, specific buggy steps. Okay, I'm stop here, and Yuchen, please go on. And please give us more examples what to digest.
Okay, sure. Right, so to the inflection point hypothesis. So the root cause of a failure execution is inferred by pinpointing the first point where the failure execution differs from a successful execution, right? So for an abstract example, we have some code here, right? Where one thread does this series of steps and then this other thread does this series of steps. So you can see that there's a condition here. So if A is not 0, then this execution is considered failed. It's a failed execution. So if we interleave the steps as such, then this execution will lead to a failure, whereas this one is a pass. So when we compare these two executions, we see that everything is the same up to this step. So the hypothesis is that, well, this is the root cause, and the tool that
by the way, but sorry for interruption. So this is I'm not sure how much you understand the Java concurrency or the concurrency program. So here, when we record the concurrent program, it means that two threads can interleave with each other. For example, those three red dots means another step from another thread, right? So they may interleave each other, but based on your example, do you mean that we need to run the program multiple times or only one time?
Right. So the way that this tool works is that you have to somehow already have a failure execution. So this is the input.
Okay,
so
okay.
It's assumed that you already have it.
Yeah. Okay, we have a failure executions, assuming that we can replicate the failure, right? So given this a concurrent program, for the concurrent program, one of the problems is that the failure may not always appear or can be replicated. We run one times, giving the schedulings, the bug may appear, but based on the other scheduling, the bug may not appear. So the assumption in this paper that we have already have a technique to steadily replicate the failure, right?
Yes.
Okay, so assume that we have a trace for the failure execution, and we have another trace for non-failure execution. And how do they find the? Yeah, my point is that since it's living, I understand you want to say it's a common prefix. Sorry. Yeah, I understand this is a common prefix, but it's possible that we have another prefix that is suppose this is blue. It's blue, 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 and red, red. It is still possible, right? It is still possible because it is interleaving programs. So in this case, it is not. It is no longer a common prefix.
Right. So you're saying that this execution is also a pass, and then so you cannot do this comparison between these two.
I'm saying that we may need to do the comparison in a more abstract way. So for example, because this thread 0 and thread 1 can interleave with each other, right? So it is possible that this A equals 0 steps happens after the second red point. It is possible if we run the non-failure execution again, if we run the non-failure version again.
Yep. So there are different ways of comparing the two. We'll get into it at the later part of the presentation.
Okay. So let me in summary. Maybe we have 2-minute noisy discussion here. The overall idea, I think the program here, is that assuming that we now a program have a bug, but we want to find its root cause, and then we know how to make it fail. So we have failed execution, and we also know that how to make it a pass. So we have a pass for non-failed executions. The idea is that we're going to align two execution trace and to find the first divergence of the execution, and the point which makes the failed execution different from the non-failed execution is considered the root cause. So this is the rationale.
Yep.
But there have a lot of technical issues here, is that how to replicate it. And my final question for these slides is that does this failure execution and the non-failure execution share the same input?
Does the failure share the same input? Yes, I believe so.
But you're not sure.
I know that for all the non-failure executions, they all share the same inputs. Yeah. So
it is.
I believe so. Like because if not, you can't really make a valuable.
Right?
You can make a reliable like inference from the two executions, right?
So basically, if we have a non-failure, suppose the failure execution and non-failure execution share the same input. So we already know what is the correct version, right? So what is correct version it is. So the non-failure version is the correct version. The only problem is that when we are running the programs, because of this concurrent or distributed systems, the trace we collected may be different from another because of the scheduling problem.
Yeah.
Okay. Yeah, we have two very similar like these, which published in TSC, but we're not addressing the distributing system problem. Okay, please go on.
Yeah. Okay. So later on we'll see that there can be so the difference about the common prefix, right? The question about that. So they have a way of defining how they choose the common prefix. Yeah, and then so I'll get into it soon. Okay. So Kairos is the tool that they developed to locate the root cause of these kind of distributed system failures in a fully automated manner. So the inputs to Kairos are the steps to reproduce the failure. And then we need to give it a failure symptom, or in other words, it's just like a point in the program where we say that, okay, this is the program's in the wrong state. So in the example that they give is the location of an exception, but actually you can choose it to be any,
I understand.
As long as you choose a line of code. Yeah,
no problem. So it means that when there's some, it means that where we observe the fault, right?
Yep. And then the other input is all the unit tests. So they will use this unit test to generate all the traces of successful executions. Yeah. So
by the way, so this unit test, if we take a set of unit tests, and those unit tests should serve as a different input, right?
Sorry.
You mean, so giving you a certain point, hello? Giving a certain point, you mean that the input for the system contains a unit tests, right?
Yeah.
The test, and each test is supposed to serve as different input for the subject system, right?
Different input for the software system.
Yeah, yeah. So suppose we have distributed systems, and these unit tests supposed to serve different input. I mean the failed execution or passing executions, or especially or the different non-failed executions. They may use different input. Am I right?
Yes, but they are determinist. Like it's defined. The inputs are defined before the tests are run already, right?
Yes. Or maybe let's go through the details later. But I'm saying that. But my point is that you're supposed to have different unit tests. So each unit test supposed to correspond to one execution, right? So one unit test will corresponding to one execution. And suppose we have two units, it means have two execution, right?
I guess so. Yes.
Test execution one, execution two.
Yep.
And suppose we have a set of unit tests. And we assume that suppose unit test one corresponding to the failed execution, and the unit test 2, 3, 4, 5. Suppose we have 5 unit tests corresponding to another 4 execution, right?
Uh-huh.
And my point is that does the unit test 2 to 5 share the same input? That question corresponding to my previous questions. If 2 to 5 does not have the input, this means that their program is designed to handle different test inputs to the system, to the target or subject system.
Okay, let me think about that. I feel like the paper itself doesn't distinguish between these kinds.
But this is a very important problem scope, whether the problem is going to address the execution from different input or the same input. They will, yeah, I think that is quite important about the problem scope. Once we enlarge the problem scope, we need a stronger technology there.
Okay, I think I know what I think I know how this pertains, right? Because later on the algorithm that they use will match up. Yeah, it will match up the context. It takes into consideration the context of the execution also. So maybe that will resolve this.
Okay, no problem. So keep going on. So okay. I just raised these questions for us to be aware that there have so whether the executions will take. So here the big question here, whether the executions share the same input or take different input.
Okay, I will go back and think about it also. Yeah. Right. So the output for this tool, right? So we will return the inflection point, and there are also a few other outputs which I'm not really sure what the purpose of it is, but it will also return a non-failure instruction sequence and the steps needed to reproduce such a sequence. Yeah. So I think it's I guess it produces an example for the developer to see how exactly.
Yeah. So basically, I think you have so I just sense that you haven't go through or fully grasped the problem definition here. So that's why we spend some time on discussing those problem scope. So I think we have a few points to remember while to keep in mind while you are presenting your this work. So the first is that the first is about the whether the execution share the same input. The second is that you mentioned for the first point, the step to reproduce the failure. And just as I mentioned, the most important problems for distributed system or concurrent system is that the failure may not always appear. So one very important technique that we need to control the scheduling, the system scheduling, operation system scheduling of the execution. So that means that means that this explains why we need the step to reproduce failure. And also, you can look at the first input and the last output, right? So I think they are exactly the same, right? The steps to reproduce failure and the steps needed to reproduce. So what's the difference between the first input and the last output?
Right, the output is a non-failure instruction sequence.
So what does it mean? And what I mean the last output, the steps needed to reproduce. What does it mean? And what is the difference between the first input?
Right. So there's actually there's a symbol here that is not showing up very nicely, but so there's it outputs a non-failure instruction sequence sigma, and then the steps needed to reproduce this sigma. So
okay, let's go through it. Let's go through it. And now that you are not fully grasped the paper, but maybe we can keep the discussion next week. Keep going on.
Okay, sure. Yeah. All right. So let me clear. Okay. Right. So the limitations to this approach is that for some failures, there's a failure execution that may produce the wrong output, but with the same sequence as a non-failure execution. So when the program tries to compare between, it compares for the common prefix, it wouldn't be able to find any. And other than that, well, the developer still needs to fix the bug, and then the failure needs to be reproducible, which is one of the assumptions. And then lastly, there can be a case of cascading failures. So what I mean by that is, like, let's say that you have some try except block, and then so perhaps it's buggy to enter inside this try block, right? But then in your error handling, there is another bug. So if you use this tool, we will only detect this last bug, but ideally you want to fix both scenarios.
That's supposed to be okay, right? So
yeah.
It means that we have two bugs in the system, and they are related. So based on this approach, they can fix the first bug, and if that bug fixed, the error may not go on, right? So that means we need to fix the second bug there.
Yeah.
So
but I guess
I mean the cascading failures can be addressed by cascading debugging tool.
Yeah, but perhaps it's not very feasible for the developer to notice also because of how they set the symptom,
Okay, let's keep going on.
Yeah. Okay, so motivating example. So this is a case for this system called the Hadoop distributed file system. And let me show you the code, right? Because it's quite a long code. So perhaps some background first. So what the distributed file system is that we have a lot of nodes, and then they all contain parts of a file. So it's a system, and then the user accesses the file system as if like it's a local file system. So they will ask for some file. And then how the system works for most distributed file systems is that you split the file up into different blocks. And then each block is replicated on all the nodes. So there's a replication factor. Let's say that you have this block A, right? And then you have a replication factor of 3. Then this block A will live on 3 different computers. Right, and then of course.
So let me specify a little bit here. Is that this is a node. This is node 1, 2, 3, 4, right? And given the Hadoop distributed system, so there's supposed to be a master slave structure, right? And then maybe this node, this file is stayed on a master, I'm not sure. So this file is lies in the master node and it's trying to just distribute the file content into different slave nodes. Is that true?
I I wouldn't say that the main purpose is to distribute. Is more like a way to be fault tolerant. So in case like if a one node is down, you're still able to reconstruct the whole file
Okay.
from what's available.
Okay.
Okay, so yeah, so of course, like let's say that there's some file B, right? So B won't be replicated on all of the same. Perhaps there's another one. And B will only be here, here, and here, perhaps. So yeah, so the idea is to split up the blocks in order to keep the system fault tolerant, right? Okay, so the reason behind all this is just to give you some context for what the code does. So in case a block is deleted, or let's say the computer goes down, and then the system needs to maintain the replication factor. So what happens is that they will replicate some blocks, right? So we will look at these need replications, some array of blocks that needs replicating, and then they will choose the target, and then it will replicate it. So how the choose target works is that right. So how it works is that it will choose a random node to replicate at. Okay, and now so we have the replication factor, which is the configuration number, and then we'll see if like this block, the block's number of replicas that it currently has, whether it is enough or not, right? So if the replication factor is more, then we need to replicate it, the difference, the number needed. So while this is true, we choose a node and then we replicate the block to this node. Right, so the error, the symptom to say is this state here, because what the users of Hadoop distributed file system realize is that when they decommission a node, the service starts to hang because not all the blocks are replicated.
Oh, well, I'm sorry. So can you repeat the bug here? So how the node, why the node is hang?
Why the what?
Yeah, you just mentioned there's a bug, right? The bug is that, and how the bug appears.
Right. So you are managing this system. You're managing this system and it has a lot of nodes. So sometimes you want to close a node. Maybe you want to take it down so that later on you want to upgrade the hardware or something. So you decommission a node. So when you decommission a node, it will delete all the blocks in that node, right?
Yes.
So yeah, so what the observed effect is that when you delete the decommission the node, there are some blocks that need replicating, but this replication monitor thread, it stops working. And the error that it outputs is this error.
The number of needed. So the problem is that when the choosing the random, the choosing target, right?
Yeah.
Choosing target, and why the bug happens?
Right. So why the bug happens is basically how the tool works also, right? So this happens because we are not able to find any node that has the capacity to house the block that needs to be replicated. And why this happens is because they use the magic literal to mark a block to be deleted. So in this case, they are marking the block size to be a maximum value. And so then obviously when you try to delete this block, no computer will have the capacity to sort of replicate it.
Let me see. The node dot capacity is this. Where the node dot. So which value is wrong? Can you specify? So this block size is wrong, or the node dot capacity is wrong.
Which item is wrong? Is it?
Yeah.
Yeah, the
So
block
the
size.
control flow. I'm asking the control flow there. I'm control flow there. So you're saying that the block dot size is assigned with the maximum value, right?
Yeah.
And then the control flow should be start from the block dot size, right? And is this block size be transformed here? Is this block size be here?
Yes. So we need to go a little bit higher here. So we pass in the size of the block that needs to be replicated inside here. Yeah, and then it passed to here, and then from here it passed to here.
Okay.
Yeah. So
so the problem is that it should not assign the max value of the block size.
Correct. So this is the problem. Yeah. So
when this one is selected, so it should assign a another. So let me repeat it. So we will have a node, and this node will keep certain replication of the block, right? Right. Suppose if the size is 3, means that it keeps 3 duplicated or duplicated blocks.
No, it's more like the block has been duplicated 3 times in the whole system.
Okay. Yes, but this is certain node, right? So I assume that this node I, right?
Yep.
So we have to know what kind of the what blocks have been kept in these nodes. When we try to redeem or delete these nodes, we need to replicate the contents in other nodes in the distributed system, right? Suppose there's other nodes, there's other nodes here. If we want to close these nodes, we have to send the nodes to other nodes, send the content or send the block content to other nodes in the system, right?
Yes.
And then now we count the logic. So when we delete the nodes and we set the block size to be the maximum value, and then we try to choosing the target and send those blocks to them, right?
Yes.
I'm understanding correct, right?
Yes.
Am I understanding?
So the replication monitor will keep looking at all these blocks, and then when they see that, right, so one is being removed, and then they will need to add it into the need replications. That list. Yeah. So indeed, so if you see if this execution happens, no, it's line 5. So when this whole program runs in between lines 33 and 34, then that's when the whole thing will throw an error. Yeah, is that okay?
I think this line 33 will not cause any error, right? It's just assignment.
Yeah.
And the problem is just may happen in this API call to remove block. And when a block is removed, they have to find a target to resign the content. Okay.
No, this need replications remove, I think, is to remove it from the set of blocks that needs replication, which is inside here, right? So if we remove it, then they will never try to replicate it. So what happens is that they are trying to replicate it before it is removed from that set.
Okay, yeah, that's okay.
Okay, yeah. So that's for the example. And so how the whole
it's better. So here in the future presentation, I suggest that And now the code itself, it is the code itself is I think code itself is hard to read. It's better to provide a few animations to construct the conceptual graph. For example, how many nodes is there, and when the node is going to close, and how we choosing the other targets to back up the content. And during the backing up, and what is error, how the error is caused. So it's better to provide such animation. It's better for us to flip graphs and save the time for discussion.
Yeah, okay, apologies for that, because
That's okay.
I didn't have enough time to make good slides.
So you're quite busy for the summer intern, right? When are summer interns ends?
31st June.
31st June, right? So it is just for within a month.
No, 31st July.
Of 3rd July, okay.
Yeah,
within two months, okay. Okay, keep going on.
Yeah, okay. So we take a little step back and then we talk about some definitions. So the root cause candidate is the location of an instruction in the failure execution where changing this instruction will result in incorrect executions that will avoid this failure. So let's say that we have some execution, and then maybe if we change the value over here, a different kind of execution, then it will follow another execution that will pass. So we consider this is a root cause candidate. But you see, sometimes perhaps like this, if we have a configuration that avoids this buggy component entirely, then that is also, you can also consider that as a root cause candidate. So what the authors of the paper did is to define this thing called a roll cause. So the roll cause of a failure is the root cause candidate that has the longest distance from the first instruction. So that gives it a bit more of a mathematical foundation to define the inflection point that they want. Yeah. Okay. So the inflection point.
I am confused on the confused here. So what's the difference between the root cause candidate and the roll cause?
Right. So
has the longest distance from the first instruction of the failure execution. So the first instruction of the failure instruction is the root cause candidate or not? Is a root cause candidate or just a root cause?
Yeah, it's possible for the first instruction to also be a root cause candidate. So maybe let's say that.
By the way, so suppose this is the first instruction. So it means the very beginning, the zero one, the step zero, the step one of the execution.
Yeah.
That's the longest distance.
Yeah. So
or the shortest distance.
No, they want the longest. So they, yeah, the furthest away. Okay.
Okay. So suppose they have multiple root cause candidates, and they want the longest. Why the longest, not the shortest?
Why the longest? Because sometimes if you choose it too far in front, it no longer pertains to the area of code that creates the failure. So an example they give is like, let's say that maybe you have some two components, right? And then the failure execution happens inside this component. Then what if I simply tell the code, not to use this component at all? I only run this component. Then in that case, the change in configuration would be a root cause candidate.
I see.
Yeah. So in order for them to avoid this discussion, they define roll cause. So yeah.
Okay.
Okay. So now the formal definition.
So here, so let me rephrase. A root cause candidate is an instruction which can divert to avoid error, right?
Yeah.
So the point is that given execution, if we suppose here is instructions, if we started executing something like exist program, suppose I exist program here, definitely the bug or the error will not happen. But this is not what we want, right? So we want to postpone the divergent point as further as possible, so that we can make the changing point or divergent point closer to the root cause, to the real root cause. And so it is called the raw cause. Am I right?
Yes, but the problem is that the root cause is what a root cause is somewhat subjective. So maybe some people would say that actually over here this is the root cause, right? So
No, yeah, I understand. I'm talking about the definition.
yeah,
The definition is that we start with a few root cause candidates, and we select the candidate which has the longest distance from the first instruction as the raw cause.
yeah.
Yeah, but
the
anyway,
definition is
but anyway, I feel that how to define the root cause candidate is still somehow a little subjective, unless they provide some formal definition.
yeah, I agree also. This one, the root cause candidate definition is something that they quoted from another paper. And yeah, it has no like formal kind of instructions on how you actually how to say like define whether this divergence is counted as a root cause. Okay. But yeah, so the formal definition for the inflection point is that it's hinging on some execution. Okay, so let's say there's execution X, and then you compare it to execution Y, and so the first instruction in X that differs from the instruction and Y, that's the inflection point. So let's say that this is some execution, and then at this point you diverge, and then this is the failure, right? And this is the pass. Then this thing here would be the inflection point.
Okay. So yeah, I think I will have a lot of questions for following slides. Keep going on.
Right. So we continue building from the definitions. So the roll cause of a failure execution will be located at the inflection point when compared to some passing execution, sigma p, where this sigma p is the execution in this set of passing executions that has the longest common prefix. So intuitively, we have a lot of passing executions, right? And then we have some failure. And so we basically compare against all of the passing executions in sigma v. And then the one that has the longest common prefix, we take the inflection point of that one compared to this longest one.
So my question is, how large is supposed to be sigma v? Or how many runtime, how many passing institutions should we prepare?
Right. So the way that they did it is that they will look at the stack trace for this failure execution, and then they will only consider the unit tests that have matching stack traces. So basically this is like quite dependent lah. There isn't a fixed limit or requirement.
Okay.
Yeah. Okay, then the hypothesis is that, well, the root cause is the roll cause. Right, so basically we have formally defined the point that we are looking for. Okay, now there's the algorithm. Okay, so this is quite long, and I'm not sure how to fully present it in the slides, so I'll just use
basically
this.
I think I think you should digest it through. You should digest it and provide animation for that.
Yeah. Okay. Maybe I'll try to do a rough run through of the algorithm, and then
Okay.
maybe next week I will provide some better animations.
Okay. Sure.
Yeah. Okay. So roughly, right, there are two things that the algorithm does that they do in order to prune the number of traces that they need. So the first thing that they do is static slicing, which is basically a static analysis on the kind of variables that causes the failure execution. So for example,
So maybe let me explain here. So the slicing is actually means the constraint data flows towards a certain program statement. So the slice physically means when it cuts something, but the nano slicing here means the query. So start from a statement like throw maybe line 28, just throw a statement, and basically the slicing can be classified as a control slicing and base slicing. For control slicing, is going to find all the if statements will influencing the target statement 28. So if we want to talk about slicing, we have to choosing a target which called a slicing criteria. For example, if we're choosing the slicing criteria of line number 28, so we find all the control statements or if conditions which can influence such a statement line 28, and the collection of those if conditions is called the control slicing. And for this slicing, it actually means it actually means what kind of the statement or the statement of the reader variables. Suppose line 28 is suppose line 27 is the criteria. We find all the statements defining the variable number needed as a state slicing. Okay. Have I explained myself? Explained myself.
Yeah. Right. So, for example, if for this case, they will see this and they say, okay, so we want to keep line 27 because line 27 leads to our failure. And then from line 27, we see that line 24 is also used. So they do both the data slicing and the control slicing, I think.
Okay.
Yeah. So they will also keep line 24. And then from there, they will create this set of locations in the code where all these like the lines are pertinent to the creation of the result of failure. All right, so that static slicing creates all locations, and then what happens next is that they will execute this. They will execute.
They only recorded those the sliced locations, right?
Yes, they will only record it at the slice locations, and then they will basically do an analysis where, let's say that for some line in the code, whether it happens and then whether it happens or not, they both result in the failure. Then they will mark this location as not useful. So they will remove all this. They call it failure agnostic or something like that. But they will mark these lines and then they create a new set. They create this new set of trace, which is called the dynamic slice. Okay, so from the dynamic slice, they group it by the threads. And then from this group, they create this thread queue. And then what the algorithm basically does is that for each series of this subset of execution, right, they will compare it against some tests in the set of unit tests, and then they will basically find the longest common prefix, and then they will start to add these executions into this final execution. Does that sort of make sense? So at first we start off with the thread that has the failure, right? And then the series of steps that that thread runs when it reaches the failure. So we start off with this queue, and then we will take some tests, and then we will compare it by the number of matching stacks. So we know that this unit test the execution in this unit test will have all these correct executions that are going to be comparable with our failing execution.
Okay, so we'll go back to the previous line one. Can we go back to line one?
Line one.
Line one here. So the unit tests here. So still my question comes to the unit tests, and are all the unit tests are the candidates of passing execution?
All of them.
I think we definitely need to answer these questions. Whether it's very hard to keep going on or keep proceeding.
I guess all the different, because what they do is they only match up against the stack. So as long as they run the same functions, all those tests will be considered.
But this, sorry. So what's your last sentence?
Right. So let's say that this failure execution.
Yeah. No. Let me ask. So we have a failure execution. So assume that. So in their proof, they assume that we have a way to replicate the failure, right? So the input of the algorithm, when the first input of the algorithm is a failure execution, right?
Yeah.
So the failure execution means a trace, or mean a set of trace. Maybe you organize the trace according to different threads, that's okay. But anyway, it's a trace, right? The trace of the failure execution. Then my question comes to the purpose of these unit tests. And the unit test, my question here is that whether all the unit tests can cause passing execution or non-failure execution.
So the failure execution, perhaps they run function 1 and then function 2 and then function 3, right? And then but some unit tests maybe run function 4 and function 5. Right. So
I understand. But anyway, at least all the unit tests are supposed to be a passing test. Right? Unit test is supposed to be pass. So you should just answer it is yes. Then from those kind of unit tests, maybe they find 100 unit tests. And it is not realistic to compare this failure execution with those 100 unit tests. Maybe we can find the 3 or 4 the most useful unit tests and taking their execution trace as a reference, right?
Yes, yep, that's what it does.
Okay.
Yeah, so sorry if I was being unclear.
Based on this idea, it means that the input of the passing or non-failure execution is different from the failure execution, right?
Yep.
Okay.
Yep. And then you can set this number of n to do the comparison against. Okay, then I will go a bit faster. So
yeah, I think we can finalize this presentation within 15 minutes.
All right, so the first, right, so we have a list of unit tests that are very close to the operations that result in the failure. So we will run and record the unit tests at the same locations that we have marked out. And then this will give us some other trace. And then now we will compare and modify our current dynamic slice with the static slice of the unit test. And then so the purpose of this part, right, is to basically add more locations into the slice. So let me give an example. Okay, so what happens is so basically in the failure execution, this line is never executed, right? But we recall that when we do the static slicing, this is part of one of the locations that we want. And then when we do dynamic slicing, now this line will be removed.
Yes.
Yeah. But in the unit test, right, we'll compare and then we'll see that actually then we only have this line that is similar. And then the inflection point is just a failure. Then it's like not useful. So what we do instead is that we have to compare and then we need to choose more intelligently, to include back some of the lines that we remove from dynamic slicing.
Okay.
Yeah. So that's where the compare and modify comes in. So we compare and then basically we get some prefix, right? And then now if the prefix is longer than what we have currently, we will update it.
Okay, so maybe we can let me call it in for explanation of the algorithms. I understand you read the papers, and my suggestion is that in your next presentation, maybe we can organize 3 sessions for the presentation in our next group meetings. My suggestion is that we let's call the end of the end of the presentation on the approach part. My suggestion is that you animalize this algorithm or turn this algorithm into animation. And you can, I suggest that you visualize what is the failure execution, since there's a motivating example, right? So giving this motivating example, you're just showing the failure execution. For example, we suppose we can replicate the failures and what the failure execution looks like, and what is unit test looks like, and what's the executions, and how do we, and it's okay that we just get rid of we just prepare a few unit tests because it is unrealistic to animate hundreds of the unit tests. Then for each conditions, you prepare a few examples. For example, you mentioned that I compare and modify. So you just prepare slides to see how what is the result of dynamic slicing, what is the result of static slicing, and why we need to do the compare and modify. So when we do the paper presentations, we focus on why instead of how. And if we're very interested in these papers, and we can just investigate to how they implement the structure. But anyway, we would like to focus on why we need a compare and modify. And for example, on line 18, why we need to further merge. It's better that we provide animations and go through these algorithms step by step. And my comments or my gut feeling here is that this approach may not work so practical. But anyway, if we want to further their studies, if we want to propose our own debugging technique for distributed systems, and this is a paper we need to refer to.
Okay. Yeah. Once again, apologies for the lack of slides.
No worries. So can we jump to the experiment? And I know that one of my comments here is that they have a very strong assumption of the reference, the unit tests. So they assume there's supposed to be hundreds, or there's a lot of the reference executions for us to reference. And once we find a reference, they assume that those reference can share informative longest common subsequence for us to debug the code and report the bug. And also they assume that the failure can be always be replicable. So in this case, they have too many assumptions, and I think in our own approach, we need to remove those assumptions one by one and to look into details. Okay, keep going on.
Okay, so I think they have this assumption because the experiments that they run are all on this kind of highly distributed and open source systems. And
by the way, so those distributed systems are based on Linux or Windows. Linux, right?
Yeah,
Usually
Linux.
Linux. Yeah. So if necessary, we can maybe Xiaoning, we can reinstall maybe 250 as a Linux system. Maybe. So in this case, we can start working on those systems instead of the doing too much on Windows system. Okay, keep going.
Okay, so the experiment is that they took some public bugs from all these very well-known distributed systems.
And
They
how
took
many bugs are they using in the experiment?
10. They only took 10, and
Only
then
took 10. So 10 is enough for SOSP. Okay.
yeah. Okay, so these are the 10 bugs, and then out of these 10, 7, they managed to find the root cause. And for the other 3 that failed, 2 of them is because there wasn't enough unit tests. So there isn't enough input, right, for the big sigma V. And then for the other one, right, is because it's because of a failure that is outside of the system. So it's an error on the disk. So they don't have this symptom to start the analysis on.
Okay.
Yeah, that's basically the results.
Okay. So thanks, Yuchen. I think we need to prepare another. I think we need to prepare another discussions. We may put it into a group meetings. Maybe we put it in individual meetings. And I do encourage you to spend more time to digest these papers. And in our follow-up work, we have some research work on basically similar. And by the other way, maybe we can have a discussion with you on your FAQ stuff. Okay. Okay, thanks. Let me summarize here. So for Yuchen's research talk, we're targeting for the automated debugging technique for distributed systems. And debugging distributed systems is supposed to be notoriously difficult. And usually debugging technique, automated debugging technique are proposed to address traditional sequential programs or the concurrent programs. So there are very few techniques are proposed to address to automate the debugging process of a distributed system. So in this approach, they are using the idea they're using the approach rationale that they want to compare two execution traces or multiple execution traces. Suppose they have a correct version of programs, they have a correct non-failure version execution and have a failure version of execution. They want to align the two execution traces and find the first divergence point. And this divergence point of these two execution traces will report as a root cause. And the experiment, I think, is a little bit insufficient to prove the effectiveness. But anyway, there is very few distributed systems they can use, and collecting bug is a no easy job there. So, given there's a technically the approach looks seemingly technically strong, and makes the acceptance of this paper. But anyway, there's a lot of some interesting technical solutions. It's lacking this presentation. I think Yuchen will complement and analyze the algorithms. And I encourage everyone to join our next presentation because it is relevant with how we do the presentation on algorithm. Okay. Thanks, Yuchen, and let's talk more later. And next one supposed to be Yufan.
Hello, let me share my screen.
Okay.
So today we will talk about a paper called Improving Neural Program Synthesis with Inferred Execution Traces. It was published on NeuIPS 2018. Actually, it was first published at the SML workshop, and then it is published on the NeuIPS. The others are Richard Shin, Ila Polosky, and Dong Song. The first other is the PhD of the Dong Song, Professor Dong Song, and they are cooperate with the called NIA. This is the company. They cooperate with this company. And their research interest is all focused on machine learning, deep learning, and security. Okay. The background of the paper is there are two terminologies. The first is what is program synthesis. Program synthesis actually is just automatically generating programs. The input of the task is the I/O. That means the input is like maybe that is the sort function, sort code, and your input will be a sequence of a number, maybe like 5, 6, 1, and the output will be the sorted number of sequence, maybe 1, 5, 6. So it's just want to generate the code of the sort. And what is the execution traces? It's very easy. In this paper, it just limit the domain to a specific language called Coral DSL. This language is quite easy. There's only this programming terminology or keyword. And
by the way, is there anyone do not understand this Bnf format? Maybe Yuchen, you can explain a few statements or how the syntax is defined. Hello? Hello, Yuchen. Oh, sorry, Yufan. Sorry. Yufan, please raise a few examples for the Bnf format. So we'll go back to the next slide.
Okay.
And this format is called a Bnf. It's called a Bnf format. So this format is usually to describe the syntax of a programming language. So usually if we want to synthesize the Java programs, the syntax of Java is very complicated. So usually for research paper, we look into some toy programming language. For example, they are using the carrier DSL. So based on this DSL program, so we're using some. So this syntax is very simple, and based on this syntax, the neural network model is going to synthesize programs which can take in the given input and generate the given output. So Yufan, will you please raise an example or explain a little bit about the syntax?
Okay, this picture is the scenario of this language. There is one, you can see this is a robot and this is a wall. In this language, it's called a marker. So this robot can move. They can move left, they can move right, they can move up, and they can move down. And then they also can move the wall, this wall, or can in this in this language, it's called they can put the map, pick the marker and put the marker. So for example, there is a very simple example, just repeat to turn right. So the traces will be turn right and then turn right. So it is just like a game. This robot, we just want to control the movement of the robot and do something about the wall. And the action trace is just in this language, they are limited to turn right, turn left, and pick and put and pick marker. So the traces is very easy. There are only 4 types of traces.
Four type of actions, right? That's more.
Oh, because I have just mentioned there are two terminology in this paper. The first is what is program synthesis, and the second is the execution traces. Actually, what is execution traces? Execution traces. They are just they are just a sequence of actions. In this paper, they define the traces as an ordered set of actions. They are sequence of actions. And in this language, the action is limited to 4 types.
So basically, think about it, because this is a toy program. Think about it. Suppose it's a Java or Python programs, and each action will corresponding to each instruction. like read a variable, write a variable, and load something from the memory, or duplicate certain things in the stack. So this is something very similar. But anyway, this is toil programs. It will be put those programs in the paper will be much easier for the user for the reader to understand.
Yeah. So here is the second question: why we use the traces? The intuition behind this paper is that recent papers have proposed neural network-based approaches to program synthesis from input-output examples. That means they just use the input and output games. But the other of these papers thinks that program synthesis from traces may be easier than synthesis from just input-output. So that means they want to change the task to the input will be traces and the output will be the code. And if the encoder decoder neural networks can synthesize programs from input-output examples, they should also be able to infer execution traces. So
I have a question here. So if we already got the traces, we can definitely define the rules to re-summarize. Suppose, for example, so suppose we already have a Bnf syntax format. So we have a schema for the syntax, and we have execution trace.
Yeah.
The difficulty level is much simpler, right? The difficult level is much simpler compared to take the input and output and synthesize programs. It's much difficult than we have the execution trace, because when we have the execution trace, it's already encode the code information there.
Yeah, but actually the trace is also unknown.
Huh? Based on your
is also unknown. So because he just generates the traces. The first step is to generate traces, and then the second step is to use traces to generate code.
I see.
So actually didn't change.
So the point is that it still have the training sample is still is input output format. So they're going to synthesize a trace, and based on trace, they could say, okay, so that makes sense.
Yeah. If based on the IO to generate the traces, and then based on the traces to generate the code. This is a two-step model, but I think it's very confused. We can first see the first step. The first step is based on the IO to get the traces model. He just use the IO pair input to a convolution and fully connect the network to get an embedding, and then input the embedding to a LSTM or RN model to get the traces. So I don't think it's a very useful.
So that means for each node it will have the input output pair. So they're supposed to have a sequence of input output pair, right?
No. Sorry, let me reorganize this picture. First, now you have one input output. You have one input, and then you want to, based on this kind of input output, to trace one kind of traces. Because the traces is a sequence, so we can definitely use the RN or LSTM model. And then he wants to embedding the IO. That means he wants to get the initial state of the LSTM, the first state of the first input of the LSTM. Then he used the IO pair to go through a convolutional network and a fully connected network to get an embedding of the IO, and then it's inputted to the first neural of the LSTM, and then he will get the first traces, the first item of the traces, and then he used the first item traces to input it to the second LSTM. So I think it just follows.
So my question here is that so this input-output embedding is used in every node in LSTM. Am I right?
Yes.
Okay, so this is and these three. Let me use another color. So these three ones are duplicated. They're exactly the same, right?
They are intermediate states. They are following these traces because this is input, and then follow the turn right. Follow the turn right action.
Okay, I see. I got it.
Yeah.
I got it. So when you generate the turn right actions, so and you will change this
state. So the state.
Think about it. So the goal here is that we want to have a trace, and the trace, the input of the, suppose this is trace, the input is supposed to be, and this is supposed to be the input, and finally after we finish execution this trace, we will have an output, right?
Yeah, yes.
We have an output, and this output is supposed to be this output.
Yeah.
And this input is supposed to be this input, right?
Yes.
And in this case, they so different inputs. They put the embedding of both input and output pair into the as initialization of the RN, right?
Yeah.
There's TN. So, but is there any alignment of the final output of the move? No.
No.
And then how do they make sure, because this trace is generated randomly, right?
Yeah.
And how do they define the failure function? How do they define the loss function?
Loss function. So first is to define the golden label, you know. Then he used the MLE to define the.
Okay, so the golden label. So when we executing this trace, so supposing that if we generate this golden trace, the input will always be. We just need to executing through this trace and compare whether this output is similar or conform to the output of the conform to the output of the trace, right?
Yes. Actually, there are different kind of golden labels. We can just back to the initial state. We now in the data set we get the IO and the
Trace.
golden code. You know, the original program synthesis problem. We have the IO and the golden code. Now he wants to change the problem to IO traces.
Golden trace.
Yeah. He wants to change it to IO traces and then golden code. So that means we need to generate the golden traces. Okay. So there are two types. The first type is just he used this model to generate the traces. And the second thing is that he used the
golden trace.
The input to the code and then use the interpreter to get the traces. There, yeah. So that
and make sure that this is exactly the same code, right?
Yeah. Yeah. He used the golden code to generate the traces. So here is the problem because when testing, there's no code actually. There's no code, no golden code. That means we must use the model to generate code.
When testing, what do you mean by when testing? So we're talking about training, right?
Yeah.
So if it is deep learning projects, we definitely have training and testing set, and all the samples and the labels are supposed to be ready.
Yes. So when training, we can use the golden traces or we can use the golden code to generate the golden traces and to use these traces to train the model. However, in the test, we can't use the golden traces because
we can put a few golden code into the testing set, right?
I don't think so. If you use the golden code, the machine,
no. So the code here is just the output. So consider this IO is an image, and the image. So in the CD program, and this code is supposed to be its label, maybe cat and dog, right?
Yeah.
So they're equivalent. So they are both look similar. So when we call this one is a sample. This is one sample, and the data set consists of thousands or tens or hundreds thousands of such sample, right? So 1 per minute. And for this data set, we can divide it into the training and testing, right?
Yes.
So in this case, we can also do the same for these programs, the IOs and the recording code. And we divided the data set into the training set and testing set.
I think this is the difference of the two steps of model. I can explain in the later because I first explain the second step, then you will understand what I'm meaning here. Because there's a two steps, you can't use the second step. I first introduced the second step. The second step is to use the traces to generate code. Actually, it is just to follow the typical model because the past model is just use the encoder and decoder to get the code. So he just follows the typical model and add traces to them. So how to add?
I didn't get it. And where are the encoder decoders?
Okay. So here is the encoder decoder. The encoder is here. This is the encoder and this is the decoder. So originally, we just have the input and output pair here. We just input the input-output embedding, just the first column. That's the second column. This second square. This part. However, in this model, he added traces. He concatenated the two embedding. The traces he used just the LSTM to embedding the traces and then added to the second this square, and then he concatenated them to input to output to a decoder. This decoder is LSTM. Is it clear?
I understand. It takes the input of the input-output and generate traces and to be seen inside the program. Yeah. And this is supposed to be your LSTM structure or transformer.
Yeah, but actually here is the decoder, and you first to encode you first to get the embedding of the execution traces and the embedding of
the embedding of the traces or embedding of each step on the trace.
Yeah, embedding of each step of the traces.
Okay.
Yeah. So this will needed to have an encoder. This encoder is actually a
it's for you one hot embedding, right?
Why is one hot embedding?
Because you can see, so each step is all either turn right, turn left, or move. So we can just provide a one hot embedding for each steps, right? But so this is very simple.
But yeah, the original you can represent turn right as a one hot, but after embedding, after the BSTM, you will get not a one hot vector.
Okay, so they try to learn an embedding, a step embedding.
Yeah, learn an embedding based on the sequence, based on the traces. This is the encoder. This is what encoders do.
And another question here is that, for example, in your code, we have some repeat while if statements, right? So so think about the trace. So suppose the trace length is supposed to be 1,000 or 10,000, right? And the code can be much concise. Maybe we only have maybe 20 lines of code to generate the trace of 10K. It is all possible, right?
Yes.
So my question is here that suppose we feed the trace of 10K steps into the LSTM, and how to design the model structure to generate a code with only maybe 20 lines of code.
In this paper, just use all the embedding. You can see in the picture the dot line.
Yeah, so I'm talking about that if it takes the embedding of each steps, it is supposed to have a very, very long trace, right? The input was supposed to be very long, or they learn embedding of the whole trace and feed them all together into it.
Each trace has embedding. Each item of the sequence trace, it will have a embedding, and he will here is each item embedding, and then he will concatenate to all the LSTM, to all the item of LSTM. You can look at the dot line.
Yeah, I understand. Suppose I'm talking about if maybe you use the term of item. I'm using the term of step. That is
Okay.
totally okay. So that means if giving a trace, there's supposed to be 10K steps. Am I right? It is
Yeah.
possible because the programs, they have a loop and they keep going on, and we have 10K steps. And so 10K steps means you have a 10K embeddings. Suppose embedding is a high dimensional vector, right? So how do we design a model structure to convert those 10K embedded vectors into to generate a program, and the program is supposed to be much concise, right? Suppose there's no one-to-one mapping relation, because based on your picture and this graph, and each trace item supposed to correspond to one tokens, or is there something I didn't understand?
Actually, he just input to every step of the LSTM. You can just see the lines. So
Okay. So
just,
I understand it. The input to every step of LSTM. Okay. So is there a limit for their trace? For example, they can only take a trace of 500.
I don't know actually, because this paper didn't say.
And based on the graph, I think that you are right. You feed every embedding of steps into the input of every cell of LSTM, right?
Yes.
Every cell of LSTM,
Yeah.
and suppose they have 10K steps or 10K items, so it's supposed to be a very huge, vector.
Oh no, they have attention mechanism. So he just all the
Or they do not concatenate, so they combine all together. They have attention
all
for
all the traces embedding item will pass through an attention mechanism and get a final traces embedding, and this final trace embedding will concat with the input output embedding. Yeah, there are two parts.
But the point is that, for example, if we write something called Y exceptions, and we do something statement like this, and different trace steps will have different importance to different synthesized statement.
Yeah.
So
he used the attention mechanism to solve this problem.
And the attention is somehow related to the positions of the cell, right? Suppose the cell here is 0, and the attention here will be different. And suppose the attention here is maybe 3, and maybe let me rephrase that. Suppose in the position of 0, does the first item or first step have a higher importance or have priority? And if we're going to synthesize the third positions, maybe the other items or steps have a higher priority to generate the token.
Yeah, maybe the attachment mechanism actually that's just a compute the similarity. That means he computed this item maybe this item's similarity of if all the traces, and if the similarity score is very high.
Wait. How could you calculate the similarity? And for now, the input is just a trace, right? And how could they compute trace? What do they need to, and what are they going to compare with? The input is trace, right? The input is just a trace. And what they're going to compare with each other? They compute the similarity with each other, or compute the similarity with something else.
What compute each other?
What are they compare the similarity?
They compare, for example, this is the first embedding of the executing traces, and this is the embedding of the first code.
The first statement, yeah.
Yeah, the first code, and then they will just use for my understanding, they are just a dot product to get the similarity of these two items to get a weight.
But you haven't got the code, right? The code is what you generated.
Yeah. They are training because the attention weight is dynamically generated. So when training, they will get a weight to like maybe x1, this is the weight, plus maybe y2 to get the final code 1. And this x is computed by the attention mechanism. And for my understanding of attention, they are just the dot product of the two items, product of one code 1 and 1. Maybe this one is just confusing. Maybe we can use that this first and this second. So this weight is computed by this dot product. This is attention mechanism, but this paper didn't talk about this thing because this is just typical attention mechanism. Hello.
Think about it. I think about how it makes sense. So let me rephrase all the things. I'm not sure. You do understand the details, right? When you read the papers.
This attention mechanism is not the detail of the paper. This is just a copy the attention paper because attention is a very useful.
That is fine. So so here the next question is that you are talking about attention or self-attention.
I'm talking about attention, not self-attention.
Okay, you are talking about attention. So
yeah.
So when you have attention, so if it is attention, there's no need for them to compare with, right? We just learn the weights, and we just learn the weights, and that's all.
Yeah, we just learn like the code repeat and compared to the turn right traces, the similarity between these two items. If the similarity is very high, this traces will weighted a lot. That means he will get a higher weight to add in the input.
Okay. So let's talk about attention mechanism. So that's just incremental ways. We can or cannot have attention in this way. Maybe have attention can have a better accuracy. So let me ask these questions. So here, the structure is going to convert the execution trace to code, right? So here, and the trace is actually a sequence of embedded vector, right?
Yeah.
And here, the model structure we're using LSTM or RF. Hello?
Hello, what's your question? Sorry.
I'm asking the model structure is using LSTM or RF or transformer.
He used a bi-LSTM.
Okay, the bidirectional LSTM.
Yeah.
Right. So
yeah.
Okay, so using bidirectional LSTM, so and for this graphic instructions, so this LSTM is this bidirectional LSTM is used to learn embeddings.
Yeah,
or not?
Encoder.
Okay. So given that, suppose we have a trace of 1K trace, assuming we have 1K trace. Anyway, there was supposed to be a limit. Suppose the limit is 1K, so the embedding, the LSTM length is supposed to be 1K, right? The length of the input length is supposed to be 1K.
Okay.
And then they apply attention techniques to learn the positions of all the traces.
To learn the position, I don't think.
Let me ask this question. So suppose there's a 1K sequence, the trace 1K, a trace of 1K length, right?
Yeah.
But the code length is not necessarily 1K, right? Suppose you're giving tokens, right? This is a token 1K. So here, but they have some padding. So if the length is too long, they will have a padding, right? So we have a lot of padding here.
Huh? I don't think so. It's an encoder-decoder architecture. This picture maybe make you feel confused. Actually, this is an encoder-decoder. So that means the input and output can have different dimension, different item of kernels, different items. The encoder first get the embedding. This is the fixed line, a fixed length, and the encoder have another fixed length. They're different.
Yes. Yeah. Okay. Yeah, that's okay. So,
Yeah.
so but anyways, even if they have a different length, they will still have paddings alongside the length, right?
Yeah. If some code.
I'm saying that suppose the trace is 1K, and the code have a limit maybe 500, right? It's possible. But anyway, not every code will have 500 tokens. Maybe some code will have only 300 tokens. So we have 200 padding, 200 padding there.
Yeah, the traces in the encoder and the the code is on the decoder. So there's no relation between these lengths.
No, I'm not talking about the relation between these lengths, but I'm talking about if the generated token, the length of generated tokens is pretty smaller, we'll always have padding there.
Yeah, maybe because the code, maybe some code will be long. It's not about some traces are long. It's about some code may be long. So that means some short
Okay,
code.
okay. So no. So we're talking about something else. So my next question is here: when we have such a trace length embeddings, and this embedding is supposed to be a fixed length, right? So you're talking about encoding decodings, and I'm talking about intermediate code, and how this intermediate code is represented.
You mean the length or the embedding? The embedding I just mentioned is the attention plus a contact with the input-output embedding.
I mean the length. I mean the length of the intermediate code.
From my understanding, they have the start symbol and the stop symbol in text generation. In the generation,
and when we it's still quite confusing when you explain this graph. So when you have so for each items or for each step where we have embeddings, and what does this graph the repeated two and squares means?
Yeah.
And how it be used here?
This is the output of the last step.
Okay.
Yeah, and the final will be a stop symbol and the output to here, and then the model will stop. So I don't know why that's the pad. There's actually no pad because it's an encode decode structure. There's no pad actually. This is a generation model. It's not a pre-trained or which we have learned before in the pre-trained like code bird. They're different. If the model generate a stop symbol, the whole generation process will stop. And the first is the start symbol here.
Okay.
Yeah, I think for text generation, this is a very typical setting. Okay. Any other question?
Somehow got it. Okay, thanks, Yufan. Please go on.
Okay, and sorry, here is the data set. It's just the same data set followed by past paper, and you can see this is a very large data set. And here is the experiment result.
Let me check the code. Let me check the code experiment data.
What?
The data. So and this data is automatically synthesized because carrier is not a very common language. So how they pick up the samples?
He just said follow the past paper, so I don't know actually.
And also how they create the input and output. So they're giving programs, they supposed to automate. They can automatically generate the input and output, right?
Yeah, maybe. This data set is just a benchmark. You can say that. So
and for each, and how many programs are there? Continuous carrier. Each entry there's they have 2.5K carrier programs, and each programs will generate 10 input and output.
Six.
Sorry, the 6, and so that means there are 6 trays. Okay.
Yeah. Okay.
It did a bit small because even for one program, say it's supposed to have a lot of input and output. Okay, please go on.
Yeah,
I just feel that if we want to let the model learn, I just feel that the data set is very small.
I think the 6 input output
Oh,
maybe small.
Yeah, it's small. Yeah, I understand.
Not small.
Yeah, I understand quantity. The quantity, the number of programs is not small.
Yeah. The input output pairs may be too small, I think. Okay, so here is the experiment result. This is quite good. We can see on the on the analysis, and in the first analysis, I think this is very useful because he just splits the data set into different kind of type, like no control flow, only condition, only loops, and with all control flow. Control flow means if, else, if, like this. And he also separates the program length. And but however, compared to the two model, first is the IO directly generates the code, and the second with add the traces at the intermediate step. We can see that the only big improve is just on the program, a long program. Yeah, just on the, I think from my understanding, the large progress is on the the much long program. But however, this paper didn't explain more. Maybe, yeah, I don't know.
I think the program space is very small. So it's easy for the model to learn it. You can see it is very simple programs. But I think the difficulty to synthesize the code for Java or Python.
Yeah.
Much harder.
Yeah, and here is the first step. The first step, IO to traces, he do an experiment, and this shows that actually I also have the confused about this step because you need first to generate the true traces, but however, this result shows that actually this model, this generate traces model is not very good actually. The exact match is not very high from my perspective. Okay, and for the second step is just I have mentioned the 2-step. Here is we needed to just explain because it's a bit different. The first is that if you use the golden traces and the inferred test, and in the test you use the inferred traces, that means this is different because in the training you can use the golden traces because you know the code. Okay, you know the golden code. However, in the test traces, you don't know the code, so you must need to use the model to generate the traces. Okay, so for this traces code models, here is the result. You can see it's not very good. However, if you in the training traces, you not use the golden traces, you use the inferred traces. That means you use the model to generate the IO to traces model just to generate this in traces. And in the test, you also inferred. Very, surprisingly, it's just bigger. That means
the point is that if we are using the inferred traces from the IO, they can have a better performance to synthesize the final code.
Yeah. However, we just see that the inferred traces is not very good. We have just see in the picture. This you can see. So I think
so where the data set shows the inferred trace is not so, the performance is not so well. So can I see the table again?
What's table?
You mean that you quote your comments, you're saying the inferred trace is not very good. So
yeah, because we have this is the first step model from IO to get the generated traces. This model shows the route shows that the generated trace is not very good. It's just
similar.
60%.
So somehow have a similar performance with this approach, right?
This is just
so here I'm going to ask questions based on this table. The press net supposed to be our approach, their approach, right?
No. This is just to show the first step model. They are not to compare because the traditional model.
Okay, so it's more like evaluation study.
Hello.
It's just like ablation studies. And so what does this no grade LGRL means?
Pardon, please. I didn't hear.
I'm saying that the no grade LGRL, it seems like ablation study. And what do these three rows means?
Oh, you mean what is this?
Yeah, so yeah, based on your slides and presentations, there's a lot of ambiguous and confusing terms here. So for example, when you're giving these tables, what do you mean by correct? And what do you mean by LGRL?
Yeah, he is just explaining the paper, but I can just explain to you. If a result to be correct, if all predict traces transform the corresponding input state to the output state when executed in the current interpreter, that means the 5 predict traces is true. That means.
What do you mean by the 5 predict traces?
Because
and give me one sample why we have 5 predict traces.
Because I don't run the code. I just imagine, because just imagine the exact match means that it's just the same traces as the golden traces, and the correct means that the first 5 predict traces is the same traces.
Okay.
Yeah, that is this paper doesn't explain very correctly.
But there's a top 1, top 10. How do you explain the top 1 and top 10?
Yeah, top 1 means that he just the first, and the top 10 means that he just search 10 example and
yeah. So, but for top 1, there's still a difference between the exact match and the correct.
What does you mean? The top
for
1
top 1, they have exact match and correct, and for top 10, they're exact match and correct, right?
Yes, right. Because the top 10 means they just search 1 traces. And the top 10 means they search.
And for search 1 traces, why there will be different? What is the difference between exact match and correct? That is my question.
Exact match means every item in the traces is exactly the same item of the golden traces.
Okay.
Yeah, the correct means the first item of the traces is just the same first item traces of the golden traces.
And why they call it correct? Suppose the trace have 1,000, have a length of 1,000, and it only be correct in the first item or first step. Why they call it correct?
I don't know actually, because he just defined this. And maybe another intuition is that if the input and the output is just the same, they will.
And how come input and output is supposed to be the same? The input is supposed to be the program input, and the output is supposed to be the output. And how could it be look like same?
No, I mean, for different traces, the input to a trace and the output of the traces are just the same as the other another traces. That means there are 2 traces. There are 2 input output, and they are same. That means maybe the traces are the same. But
so I suggest that so when you do the presentations, I suggest you try to find some other students, maybe Xiangling or Yufan, to rehearsal for you, so that and also you can see that for the oral English, you also need to improve your expressiveness. And also there's supposed a lot of details. When you do the presentations, we're supposed to learn something from it, but there's still a lot of questions revolving around it. And which means that not everyone can benefit from your efforts. You pay the effort, you understand the details, but I said you need to find a way to articulate and clarify many details. And also, so for example, when I ask the question, do you think those details important?
I think this are just a setting. You can have different metric, and these metrics are setting by the.
So the point is that so I suggest that when you prepare the slides, you make your slides self-contained, and so that people can learn something here. So when you put the slides here, there's a lot of questions revolving around here, and including no grades in LGRL. I suppose there's a lot of information is missing. But when you provide the slides, you're supposed to, for example, Yuchen cannot spend a lot of time. You will admit that some part is not unclear. If it is unclear, we do not waste the time. So we just stop. We just wait for a better preparations and to represent. But here, do you think you really fully grasp the correct top 1, top 10, and what is no grades and what is LGRL?
Because these performances are very similar, so I don't think it's important thing. But if you feel curious about these things, they are actually just
you're supposed to be fully grasp the paper so that you can address a lot of questions.
Okay, so the LGR is the convolutional encoder, and if he add a residual connection between the layers, he will say it's as this model. They are just quite similar. This actually the difference is not very interesting actually.
So here, so why do you say that the performance of inferred trace is not very good?
Because you can see that the exact match is very low. That means the model would generate a wrong traces. Could you get it?
Got it. But different traces may still have the same semantics, right?
Yeah. So this is because this is why he used the correct maybe for
so they define it correct.
Yeah,
so,
but
so if I'm the one, so I will tolerate the mistakes or error within certain bound. For example, even if the model does not generate 100% accurate traces, but if the traces is still similar to the golden trace, we may still consider it correct. But giving your onset, you're saying that as long as the trace have the first item or first step same to the golden trace, it will consider it correct. I really doubt it and I'm quite confused why they have such a design. And you know that this paper has been accepted in the NeuIPS. So this is a top tier AI conference, right?
Yeah, I also think this paper is not very innovation actually, but I think this correct me is you just follow the typical setting. Because this paper doesn't explain very clearly. He just one sentence to explain. I just mentioned.
I suggested so maybe we should call it a day for today's presentations. I think it is almost the end of the presentation. I suggest you learn from Zhang and Yufan's presentation. Their videos is always is online. You can learn how they organize the slides and articulate and clarify those details. That is very important. Okay.
Okay.
Okay, so maybe I can have a few comments here. If I will please go to the model architecture there. Yeah, so here, so I think the novelty here is that I'm going to synthesize trace. But anyway, since the trace itself is including more semantic meanings, and these two steps architectures might actually present some novelty to me as well, but there's still some something unclear to me as well. So usually if we want to synthesize the programs, maybe starting from the trace is an interesting problem. And also there's something interesting to me is that embedding of trace. So when we are talking about program analysis, embedding the code, but very few approach are looking to the embedding of trace. And that will also facilitate a lot of interesting applications like debugging and testing sectors. Oh, by the way, Yufan and Yuchen, would you please share your slides in our group?
Okay.
Okay, so maybe we can call it days. Is there any question there? I think there's still something unclear that, but it's good for you to raise your questions. You cannot fully, I think we cannot fully grasp those slides until we involve them into discussion. So when given this topic, and also like Yuchen and Yufan, I suggest when you are preparing the slides, you take it as an opportunity to practice your presentations. For example, how to organize the slides to raise the curiosity and the interest from all audience, not from me. Because I'm the one who organizes, and I'm the one who is responsible to keep the curiosity and raise the questions. But for other audience, and how to make your slides and presentations more attractive and interested instead of let other students get to sleep or close the audience to look something else. So that is very interesting. To improve your presentation skill is also very, very important. You can see the first slide is that how to automate debugging. And debugging is a progress lingering on almost all of us. And everyone programs, everyone writes bugs. And how to, if there's a tool to automatically find the bug for us, it is very, very useful. And also, Yufan's work, Yufan's presentation is talking about how to synthesize the programs just based on the input and output. So there is also a very magic-like approach. But of course, so these topics is better for you to write more stories, present the motivating examples, especially for fun. You are a PhD student and you will write papers, and especially for not software engineering papers, how to writing intriguing and motivating examples is really important. So taking this opportunity to organize the slides to raise interest of all audience, it is a really important skill.
Okay, actually, I have some comment on the PowerPoint slides, so
Okay.
you can check if you don't know the terminology like exact match correct. I just added the explanation in the paper, but actually I also didn't quite understand what he said, so I just add on the comment part.
Okay. So maybe is there any questions here? If there's no other questions, let me call it a day, and I'm going to close the session. Okay, it seems there's no such questions. Let's end the session then. Bye, everyone.
Bye.